This is your instructor, Guy Mansfield, and I want to thank everybody for being brave enough to return for our second module in the series. Let's go ahead and get started. Just a reminder on housekeeping. We request everybody please mute your input, and then we do welcome questions. If you have questions, use the chat window, and our moderators, June and Suzanne, will help me see those questions as they pop up. So again, we do welcome questions. And then let's see. Okay, that looks all right. Let's go ahead. So as I said, this is the second module in our series on search theory for canine teams. And as I think I mentioned earlier, our intent with the series is not to make you all search theory experts, but to familiarize you with how search planners may use those concepts to define and prioritize canine team assignments. And again, I need to give credit to those who I have learned from, Hugh Dower, Skip Stoffel and his son Brett, Dr. Don Cooper and Dr. Bob Kester, and others who've been leading the teaching of search planning for many years. And as I've said before, those folks are the experts, and I'm merely a storyteller in all of this. So in tonight's module, I'm going to introduce and examine search theory concepts that help us quantify how effective our searching has been. And as we do this, just keep a couple of thoughts in mind. We're going to be using concepts of probability to quantify uncertainty. And remember, the fundamental uncertainty is that we don't know where our subject is. I think it's also important to keep in mind that when we're using search theory concepts, what we're doing is we're building a model of this uncertainty. And if our assumptions are really good, our model might be a good approximation of reality. But remember, it's just an approximation. It's just a model. So let's do a quick review of our 3 sessions. So in Module 1, I introduced concepts that help us understand the question, help us answer the question, where should we search? And where should we search first? And as I mentioned, the objective was to provide sort of the background context that helps us answer the question that I'm sure all of us have asked, which is why the heck are they sending us here? So in Module 2, we'll cover concepts that help planners know how effective searching has been for both humans and canine searchers. And then in Module 3, there I'll introduce some thinking we've been doing on how to apply search theory concepts to searching for human remains or evidence searches. But first, we'll break things open tonight and see if our first poll works. And we're going to launch a poll about clearing GPS tracks. So let's see if the poll launches now. And if you can see the poll, go ahead and start answering. I can see folks have started answering. All right, and with over 70% of the votes in, we're going to call the results here, and most people respond that they forget to clear their GPS tracks only when rushed. Let's see if I can share the results here. Although some folks said that they hardly ever forgot to clear their tracks. Okay, that's good. All right, so back to the the nuts and bolts. I will start with a quick review of the basic concepts covered in Module 1. That was probability density and probability of area. We're then going to turn to revisit the concept of sweep width and look at that a little bit more closely because we'll see that the concept of sweep width is actually fundamental for quantifying search effectiveness. It's really another one of those foundational concepts in search theory. Then after that, we're going to see how sweep width is used to calculate what's called coverage. And then we'll see how coverage can be converted into probability of detection. And then lastly, we'll see how probability of detection is used to quantify how much probability has been searched out of an area. So those who took careful notes during our first session will remember this diagram. And let's quickly review our search planning cycle. We begin by gathering information, speculating about specific scenarios, combining that with terrain analysis, and define search regions and areas. We make initial statements about probability of area. Then to complete the cycle, we actually go out into the world and search. And then we'll see tonight how we use that experience to calculate probability of detection and cycle back to compute how our initial area POAs change. I'll repeat my general reminder that there really is a ton of complex math underlying search theory, but fortunately for us, it can be understood and used without needing to jump down and into all that math. All right, quick review of the concept of probability of area. And remember that POA is our estimate of the likelihood that our subject or what we're looking for is inside a particular search region or search segment. Here we've shown 4 search regions, and in this diagram, regions A and B have POAs of 40. Regions C and D have POAs of 10. And if we prioritized our search based on probability of area alone, we'd rank regions A and B equally. Okay, so far so good. All right. We also saw that the concept of probability density quantifies not only how many units of probability are in a region, but how tightly packed or concentrated they are. So if you look at regions A and B, you can see they both have POAs of 40, but because region B is a much smaller area, those 40 units of probability are packed much more densely in region B. And so probability density, which is abbreviated as Pden, is simply calculated by dividing the POA over the area. And for that region, we saw that region B here in this example is a much richer probability environment. So if we had limited resources and a limited amount of time, we would want to prioritize searching in region B higher than searching in region A. We also saw that once we have probability density for a search segment, we can combine that with estimated team speed and sweep width to calculate what's called probable success rate, or PSR. In Module 1, we use this sophisticated mathematical diagram here, this little Pac-Man search team, to show that PSR is a way of forecasting the amount of units of probability they're going to be gobbled up as the search team works their way through the search area. And so the point we're trying to illustrate here is that PSR is a way of forecasting the amount of units of probability that could be swept up per unit time as the search team proceeds. And excuse me, we saw that prioritizing a list of search segments by PSR is a more efficient way to assign limited resources. It's a way that we can maximize the chance of finding our subject in the least amount of time. All right, before going into new territory, a quick review of the overall map. What we've just seen is we begin by deriving or estimating a probability of area for search regions and segments. And then we can calculate the probability of density. And then if we have a way to estimate sweep width and team speed, we can calculate PSR, probable success rate, as a model of how effective a search team's going to be. And all of these helped us answer the question, where should we search first? Now we're going to add to this picture. We're going to return to sweep width and look at that in a little bit more detail. Then we'll see how the concept of sweep width allows us to take several steps and calculate coverage and then probability of detection. And lastly, we'll see how POD allows us to model how effective our searching has been. Okay. All right. So now let's revisit sweep width, and we're probably going to do this in more detail than anyone will enjoy, but it's, again, it's a foundational concept. And you'll also see it's referred to sometimes as estimated sweep width. That's why we've got ESW here. So we saw in Module 1 that sweep width is a measure of side-to-side detection width of a searcher. And that applies to humans or canines, or in fact, drones or UAVs for that matter. So let's quickly review the ugly, the bad, and the good about sweep width. And the ugly, of course, is that it's based on pretty complex mathematics. And the bad is that it's very difficult to measure it accurately. And the really bad is it's very difficult to measure it for canines. But the good news is that sweep width, at least for humans, can be estimated with a relatively simple field exercise. And I'll just show you an example of that. But what's important about sweep width and why we're going to be spending so much time on it is, like I said, you'll see that it's foundational for getting us to probability of detection. All right, so let's see what's on the next slide, and this will look pretty similar. All right, so we're going to continue our review here. And remember, when searchers move through an area, one of two things happens. Either we find the subject, or the probability that the subject is in a particular area is reduced. And so in looking at this diagram, you can think of these little yellow dots as representing either findable objects or units of probability. And like I said, sweep width is a model of how broad a swath of area is swept out during a search path. And notice and remember, it also takes into account that search sensors are not perfect. And you can see that some of these little units of probability are left behind. It's not a clean sweep. And I'll mention here that sweep width is not necessarily the same as searcher spacing. That's a whole sort of complicated discussion that we won't be getting into tonight. They can be related, but they're not the same. All right, so let's use this slide to think about sweep widths for different types of search sensors. And it makes sense that different types of search sensors looking for different types of targets in different terrains are going to have different sweep widths. They're going to have a different ability to detect things at distances. So an air scent canine searching under good conditions may have an extremely wide sweep width when looking for this lost child. In contrast, humans looking for the same lost child under the same conditions are going to have a narrower sweep width. If we're searching for the lost child in thick woods, that sweep width could be even narrower. Or if it's canine searching for old bones or small amounts of human remains, that sweep width may be only a few feet or even less. As I mentioned earlier, for human searchers, and this is nice, there's a quick and reasonable way to get an estimate of sweep width, and it's called average range of detection exercise. It takes about 5 minutes and can be easily taught. It's similar to other techniques. For example, some of you may have heard of the Northumberland rain dance, as people like to call it. But this is an exercise that can be done by teams just as they enter their search segment or their assigned search area, or it could even be done by search planners in advance. Excuse me. And in the AROD exercise, what searchers do is to, through a walk on the ground exercise, is they determine detection distances to a target object. And the way it works is sort of shown in this diagram. A suitable target object is selected and placed in a reasonable location. And then ideally, 8 team members, or it can be done in pairs, will walk away on a compass direction. And usually this is done in opposite directions. So you have person A going north and person B going south. And they walk in their own direction, checking until they can no longer see the object. They turn around and they come back on that same reverse bearing until they can see the object. And then they count paces to measure distance between where they could just see the object and the actual location. And each team member does this from different directions, yielding a bunch of different detection ranges, which are then all averaged together. And occasionally there's a correction factor used, which I won't go into. But this yields, and it's been shown to yield by some research, a pretty darn good estimate of the sweep width under actual field conditions. So, for example, prior to some recent large-scale evidence searches in Eastern Washington, we actually went out in advance and performed AROD exercises on site. And we selected representative terrain in the area. For example, there was forested, or well, not forested, but sort of open terrain, but also we treated rocky field terrain as something totally different. So we did AROD exercises in these 2 different representative areas. Took us about 10 minutes to complete the exercise, which provided us with estimated sweep widths that we could use to model or forecast searching effectiveness. Now I should mention that for human searchers, selecting a target object or what to use for your AROD exercise can be an interesting exercise. And it requires a little bit of thinking. So if you're looking for a child, maybe use a small pack. If you're looking for a body or a person who you think might be down, maybe use a pack as well. If you're looking for bones or remains, this starts to get a little bit trickier. And for this particular search, we used a small stick, but that was sort of a squishy call on our part. It requires some thought. All right, so let's see. So estimating sweep width for our canine buddies, though, is a bit more challenging. So let's first think about canine sweep width in the ideal world. And in that ideal world, magically, we would know the exact sweep width for every individual dog under all conditions of terrain and weather. And we would just plug that sweep width in and we'd also have values of team speed, exact values, and we'd be able to calculate this exact absolute value of probable success rate for each search segment, and we were really happy about that. Unfortunately, we don't live in an ideal world, so we need to think about possible alternatives. In general, there are 3 ways to come up with or estimate sweep width. The first way is by performing careful field experiments, not the quick AROD exercises, but very careful, extensive field experiments. And these yield good results, but are very tedious and pretty impractical. Second method is by the quick field exercises that I mentioned, the AROD exercises. And like I said, this is practical for most searches, works well for human searchers, but it really is not practical for canines. At least in my imagination, it's not. The third method is you just make a subjective guess. You pick what you think is a reasonable sweep width. Now, of these 3 methods, this is clearly it's the sloppiest and the least preferred. But that being said, if you guess sweep width values consistently and you use those in your PSR calculations, those values will at least provide a valid relative ranking of search segments. So for example, it was about a week or so ago, we were supporting searching at Mount Rainier up in forest areas, in many places blanketed with snow. And I think I mentioned this, it was a little bit too hazardous to have actually people go in different directions to do an AROD exercise. So we actually just plugged in an estimated value for sweep width and team speed and used those values consistently across all search segments, which allowed us to be reasonably okay with the relative rankings that we got. Now, those of you who are really sharp in math and are thinking back to the formula have realized that basically if we used constants for the sweep width value and the team speed value, we were basically sorting those areas by probability density, which is okay. All right. Okay. All right. Oh, let's see. So it's time for another poll here. And what we want to do is think back about your experience with your canine looking for live subjects. And think about the distances at which your canine has detected a live subject. So let's see if I can bring this poll up. And launch. Okay, so polling is launched. So everybody think about your experience and jump in and we'll see what the answers are. Okay, I can see we've got almost 60% of people voted. Things are slowing down a little bit. Okay, let's wrap things up and share the results. And what do we see here? We see that most of our folks, excuse me, report that they've experienced their dogs detecting subjects over 100 yards away or over 500 yards away, with a couple quite a distance, over 1,000 yards away. Okay, that's very good. Now let's ask a similar question, but now where your dog has been out searching for HRD source or remains. So let's start that next poll, which I think is this one. Here we go. All right. And here you notice we're assuming that the detection distances are much, much narrower. All right, so polling is sort of slowed down. So let's share the results here and see what we see. And here it's interesting, our answers are much more distributed. We've got a distribution of percentage answers. It's like within 10 feet, within 50 feet, 100 feet away, and some even over 100 feet away. So quite a variety, and I expect that reflects a range of conditions and what's being looked for there. Okay. All right, so let's go back here. And I did a little bit of looking for scientific studies on canine sweep width, and there's not much out there. So it's not my intention to dive into this topic in this session, but I'll just mention and describe one example of a carefully done study reported by Glenn and his colleagues. And this took place in New Zealand, and they used wildlife detection dogs. And it was a pretty well-designed study. I actually read through it, which is pretty tedious. And what they did was that they placed dead rats at different distances from a fence line. And then they had the dogs walk the fence line and measured the success rate at each distance. In other words, what percent of the rats at the close distance were detected versus what percent at the longer distances. And then they ran this through a mathematical model. Incidentally, it was the same mathematical model that people use when they're measuring human sweep width. And then under these conditions, they derived a average estimated sweep width of about 17 meters. Okay, so clearly this won't apply to all of our search conditions, but perhaps this is a starting point for estimation purposes. So I now want to propose a homework assignment, a thought experiment to take home with you. And the general question is, can we use logic and observations and assumptions or even additional data to extrapolate from the results from Glenn's study to estimate some relative sweep width values for different HRD targets? For example, and this might be a little bit fanciful, if we were looking for not a small dead rat, but actually large source outdoors, a whole body perhaps, would it be reasonable to multiply Glenn's 17 meters by some sort of ratio of rat to human body weight or surface areas? Well, maybe yes, maybe no. I don't know the answer to that. So, but it's anyway, I just, I'll leave that with you as a thought experiment to take home with you. We can't dive into this tonight, even though it's a fascinating topic, because we'd never get home. All right. So back to not being in an ideal world, can we still use search theory concepts? Can we still use the concept of sweep width for modeling our canine search effectiveness? And I think there are at least two camps on this issue. One camp would say there's just too much variability in dogs and terrain and wind and weather and search conditions that you just can't predict canine sweep width. I'm in the other camp, which holds that it's for now, until we get better studies done, we could at least assume an average canine sweep width for our search conditions. And we could, just as we made assumption about average sweep width for human searchers on our Mount Rainier search. And we can assume that, just as we do for human searchers, that variability between dogs and different conditions will sort of average out over time, over search segments, and that we can still calculate a probable success rate that will be a relative, allow us to understand the relative differences of forecast effectiveness across search segments. Okay. So now that we've reviewed sweep width extensively, let's move a little bit farther to see how sweep width allows us to then calculate what's called area effectively swept, and then coverage, and then probability of detection, and then to cycle back and adjust our initial assumptions about probability of area. All right, so now we're going to dive into the concept of probability of detection. We know, and it's abbreviated as POD. And in the past, POD has been estimated subjectively based on the team's interpretation of their experience on the ground. And I think most of us will remember being asked, well, what's the likelihood that you or your dog would have located the subject had they been in your assigned area? And we've all answered, well, it was dark and swampy and we couldn't see our hand in front of our face and it was too hot for my dog. But I think our POD might have been about 50%. Now, actual research has shown that these type of subjective estimates are actually unreliable. So in modern search theory, we don't use those. And POD is calculated using more objective factors. And the more objective way to think about POD is to ask the question, how much probability has our searcher or search team removed from their assigned area? And remember, as search teams move through an area, they're gobbling up or sweeping out units of probability. And what we'll see is that we can actually calculate how much probability has been swept out. So this involves several steps, and so I'm going to go through these pretty slowly, one at a time. As a first step, we're going to look at how we get to the concept of area effectively swept, which basically is how much area has our search team covered, okay? And here's where our old friend sweep width becomes important, all right? So as I just said, as our search team is moving through, they're sweeping out this path, gobbling up the units of probability. And we want to calculate the area of that path. So that's pretty simple. And we'll remember back from basic math in high school or grade school, I guess it was, that we never thought we would use again. If we want to get the area of a rectangle or a long piece of spaghetti, we simply take the length times the width. And for width, we use estimated sweep width. And for length, we simply use the length of the path that the team followed. So the formula for area effectively swept is simply track line length, that's TLL, times sweep width. And then if we have multiple searchers on the team, each person gets credit. So we would also put in a factor for multiplying it times the number of searchers on the team. All right. So this explains why we'll always be bugging you to get high quality GPS tracks for both you and your dog. And what we do is we process and measure those GPS tracks to accurately measure the length of travel within your assigned search segment. And that allows us to do the math that gets us to area effectively swept. So this map on the right is from an actual study. This is from the now not quite world famous Search for the Missing Russian. And throughout multiple operational periods, we collected and plotted tracks for both human searchers and dogs. And I think green are the dogs here and purple are for the human. And we'll show you in a minute how we use those on the way to calculating POD. So again, this is why, this is why it's important when we ask you to clear your tracks just prior to starting your assigned search area. Otherwise, we get a track that starts here and then has a 200-mile length line off the map and goes all the way back to Seattle where you started. Okay, so let's pause for a minute now on this slide to visualize canine and human tracks. On the left here, we see a canine handler track, that's the red line, and a canine track in blue ranging around the handler. Or for some dogs, they're doing orbits, okay? And let me pause here because I saw a question, which I'll try to, we had a question. So if we multiply back to, let's see, I need to back up a slide. So the question is, if we multiply times the number of searchers, doesn't that assume there's no overlap between multiple searchers? Okay, so this is a really good question. And I'll give an answer to it, which may not satisfy everybody. Certainly it didn't satisfy me for a while. Because in the early search theory classes I attended, I asked the same question. And the search theory answer is that it doesn't matter where the individuals are traveling. It doesn't matter if they overlap or cross paths or in fact walk along in the same line. Every single one of those, no matter where their track goes, gets credit for their track line length. So that's the short answer. And there are longer discussions behind that that I just won't go into tonight. So I hope that's at least partially a satisfying answer. Okay. So back to visualizing the canine and human track length. So you can see that this is one of the reasons we process the canine track differently from the human track. Obviously, the track line length is going to be different. On the right here, we've stylized a representation of sweep width for the same search. And, you know, no surprise again, the sweep width for the handler is relatively narrow, whereas the sweep width for the canine's path is relatively wide. And incidentally, I was looking at this right side of the slide earlier this week, and what I realized was is in this one diagram, it basically illustrates why search dogs are so valuable. So, but anyway, that's why we will collect tracks and process them separately for the handler and for the canine. And we will compute area effectively swept separately for them, and then we'll count or combine those in overall coverage. So a question has popped up. What do we use to collect tracks for canines? What the method that I'm familiar with that works very well is that the teams I've been on or associated with use Garmin Alpha collars. So that's a collar on the canine which has a little GPS receiver on it. So that little GPS receiver knows where the dog is, and it's recording a GPS track. And then incidentally, if you set it up correctly, it will transmit that information in real time to the handler, who is looking at a little screen on their handheld unit and can see where the dog is and other important things. So it's a really, really good setup. So, alrighty. So back to the next slide, I think. Yes, okay. So now, so that's once we have area effectively swept, and again, that's sort of the pink area, swath that's been gobbled up by our little Pac-Man, okay? We now want to get to the concept of coverage, which is a pretty simple concept. And that simply is, what's the proportion, what proportion of the entire search segment does the pink path represent, okay? And we get that simply by dividing the area effectively swept by the size of the assigned search segment, and it'll come out like a percentage. So for example, if our search team swept out 25 acres and their segment size was 50 acres, that would be a coverage of 50%. So that's fairly straightforward. All right, so now comes a tricky step. How do we get from percent coverage to probability of detection? So here we need to rely on earlier research that showed a mathematical function that relates coverage to probability of detection. And it's shown as a curve on this chart, and there's actually a formula behind it that we use. And let's look at an example. If we have a coverage of 100% or 1.0 here, I think I've got a little arrow, yeah. What we do is we read up until we hit the curve, and then we read over to read our probability of detection, okay? So here we had a coverage of 100%, and that yields a POD of about 62%. Well, I'm hoping some people are thinking, hang on a minute, if we covered 100% of our search segment, how come our POD is only 62%? The main reason is because, remember, POD is calculated based on sweep width, which models imperfect search sensors. It models sensors that are going to miss some of the potential probability targets as they're searching. Okay. All right. So that's conceptually how we get to sweep width. Let's actually go through the steps of calculating this. And again, not because I expect you guys to be doing this in the field, but just to give you a little bit better feel for it. Excuse me. So first, imagine we're searching a 100-meter by 100-meter square right here, okay? So the total area of this square is going to be 10,000 square meters. And we've estimated our sweep width to be 10 meters, or about 30 feet across. So in this simple example, one searcher sort of grids or works his way back and forth about 6 times and ends up with traveling a total distance of 700 meters. So our track line length here is 700 meters. Now we just apply the formula. Let's do the math. Area effectively swept is going to be the 10-meter sweep width times one searcher times a track line length of 700 meters, which gives us 7,000 square meters. Coverage then is 7,000 square meters over 10,000 square meters, or about 70% coverage. we go to our coverage and POD function chart, and we read up from 70% coverage to see that our POD was about 50% here. And that's an example of starting at using sweep width and combining that with track line length and getting all the way to probability of detection. Okay. Now, in the real world, we don't carry this chart with us, but we have this formula that describes this curve embedded in an Excel spreadsheet. And so we just plug the numbers in and it calculates that for us. Okay. So now we know how to calculate POD, and we can now look at how it's used to quantify search effectiveness. Sort of a long road to get to this point. So remember, again, when a search team searches an area, one of two things happens. Either the subject is found or the likelihood that the subject is in that area is reduced. So in the example shown here for search segment 1, the starting POA is 40. We search that area and we calculate that the POD is 50%. So the way to think about this is that that searching has removed 50% of the original POA. Okay, so a little bit of math, 50% of 40 is 20. So the leftover or residual POA is going to be 40 minus 20, or 20 POA units left over. And that's an example of how we calculate how much probability has been searched out of an area. Okay, that's that POD of 50% searches out 20 units of probability. And that's how we calculate how much probability is left over after a search sortie. Okay. So now let's look at how search planners use this to get from one operational period to the next, okay? And what we do is, like I said, we use POD as a figure that quantifies the amount of probability that's been searched out of each segment, okay? And as I've described before, after each operational period, we collect those GPS tracks I talked about, and we calculate the POD for each search segment. And then we calculate the residual POA for each search segment. And then we can take that residual POA, and if we need to then, for planning for operational period next, we throw that into our calculations of probability density and probable success rate as a new starting POA, if you will, to help us prioritize where to search next. Okay. So I'm gonna repeat that. So the main purpose of collecting those tracks, calculating POD, calculating residual POA is in a multi-operational period search. It helps provide a better answer to the question, where should we search next?
I have a couple of questions, one from Keith and one from Ivan.
Okay, from Keith. Any good ratio for handler to canine coverage? I'm studying this question. So typically my canine is between 3 to 4 to 1. I think Keith is asking, is there a cosmic average good ratio for perhaps the distance traveled by the canine versus the distance traveled by a handler? Yeah. And I'm not a handler, so I don't know the answer to that question. There may be sort of an average, or it could be that if you ask 10 handlers about that, it would result in a spaghetti fight. So the short answer is I don't know the answer to that. But it's something that we can observe rather quickly by looking at those GPS tracks that we get back. So let's see, from a question, I thought POA was a probability that the subject is in an area instead of a probability of finding. That's correct. POA is your estimated probability that a subject is in a particular area. It's possible I got a little bit loose with my terminology there, but yes, that's correct. Okay. All right, so moving on a little bit. Okay, so here, this is an example. It's a pictorial representation of how we used or represented this concept of residual probability of area in the search for the missing Russian. And on what we did was we prepared sort of a schematic map, and in that we highlighted and color-coded search segments with a high residual probability of area and little previous searching. And we simply presented this as sort of a quick digest for the incident commander. So we said, look, if you look at these red or pink areas, based on the searching to date, these are the areas that we'd recommend that we put resources back into. Okay. Now, for this search, we combined the POD calculations with some other factors, but this gives you an idea of how that can be used. Okay. Let's see. All right. So we've just covered a whole bunch of steps getting from sweep width to area effectively swept, through coverage, through POD and residual POA, which is a whole series of steps. So let me pause here and see if any questions come to mind on that. Pause for just a couple seconds here, I guess. All right, so either everybody's okay or everybody is has totally lost. Let's hope not. Okay. So a couple final points. So in a protracted search with multiple operational periods, again, such as the search for the missing Russian, which went through, if I remember correctly, 8 or 9 operational periods, we can quantify how probability of area for our entire search area decreases over time. So we can see, if we take a look at the blue line at the beginning of the search, the total cumulative POA is going to start at 100% because, you know, we believe the subject is in somewhere in one of our search regions. And as we go through each operational period, calculate POD and subtract that from the starting POA, we can see that the remaining probability of area gets less and less. There's sort of a mirror image concepts that search planners will sometimes use. I'll just mention it. It's called probability of success. And you can think of that as the amount of probability that's been searched out of all of your search areas through different operational periods. And you can see how that accumulates over time. And these two views, either the cumulative POA or cumulative POS, can be used by incident commanders and search commanders, search managers in 2 ways. One, to decide if maybe they should increase the search area boundary to other areas, or 2, to decide if the search should be terminated or scaled back. All right. So I'll close with a review of what we've seen so far and what we've covered tonight. Okay, we begin by seeing that the probability of area and probability density could characterize the amount and the density of probability in a search area. And we saw that we could also use the concept of sweep width to estimate how much probability is swept out of an area during a search path. And we saw how sweep width could be used along with estimated team speed to calculate probable success rate, a forecast of how effective teams are going to be. Then we saw how sweep width combined with track line length or the length of travel of a search team would allow us to go through area effectively swept and calculate the percent coverage and then calculate POD and use that POD as a measure of how much probability has been searched out of an area so that we could calculate the residual probability in each search region or search segment, and then feed that picture back to reprioritize assignments for the next operational period. All right, so that's the summary of the material that we've gone through tonight. And I'll stop at this point, and we'll have time for several handfuls of questions if there are questions. And again, just type those into chat and we'll be looking for those.